Hi, I am Wasim Shahzad from National University of Sciences and Technology, Islamabad, Pakistan, and I will be presenting my research work which is about characterizing the effect of motion class taxonomy on the performance of hand motion classifiers. These are the contents of the presentation. Intuitive control of active upper limb prosthesis is still a dream despite decades of research. Although pattern recognition of electromyography signals offers a promising solution for intuitive prosthesis control. However, the academic success of PR-based control is yet to become a clinical reality. PR-based classifiers are mostly evaluated by testing and training for a limited number of motion classes, which fail to capture the variability of human grasp taxonomy. The fundamental thought to action process starts in the brain. When we think to perform an action, the brain sends the necessary command signals to the muscles through the neurons. As a result, an electrophysiological process causes the muscles to expand or contract, resulting in the desired motion class. The electrophysiological process also causes electromyographic signals, which can be processed to classify muscle activity. A number of researchers have studied the basic grasp taxonomy. In a preliminary study, Katkowski established the hierarchy of 16 different grasp patterns on the basis of 9 different parameters including connectivity, grasp isotropy, resistance to slipping, and a number of other parameters. Bullock et al. Categorized manipulation tasks into 15 simple categories using object-centric, environment-centric, and hand-centric approaches. Feeks et al. Categorized motion classes into 4 categories on the basis of finger and thumb position and grasp force. Stivell et al. Divided grasp types into 5 categories based on grasp shape, finger positioning, and muscular activation patterns. For example, Stivell et al. Established the 5 different categories by utilizing the edit distance metric. Now, the previous studies have focused on establishing the hierarchy of the grasp types. However, the effects of motion class taxonomy on classifier performance are yet to be evaluated. The purpose of this research is to study the effects of motion class taxonomy on the performance of PR-based hand motion classifiers, performance comparison of SVM and LDA classifiers in classifying various taxonomical groups, and to study inter-subject and inter-class variability of different taxonomical groups. A data acquisition system was designed to achieve these objectives. 4 custom-designed SEMG electrodes were sampled by a 32-bit ARM Cortex-M4F microcontroller. The 4-channel data was then wirelessly transmitted to a personal computer for data logging and processing. Experimental data pertaining to 16 motion classes was sampled from 9 healthy male subjects. The 16 motion classes were divided into 2 taxonomical groups. The distant taxonomy motion classes consisted of classes which were taxonomically opposite to one another. For example, open, close, extension, flexion, ulnar deviation, radial deviation, pronation, and supination. The closed taxonomy motion classes consisted of classes which are taxonomically similar to one another. For example, cylindrical, tripod, lateral, quadpod, pinch, spherical, precision spherical, and fixed hook. The 4-channel raw SEMG signals were sampled at 1 kHz and digitized by a 12-bit ADC. Data was segmented using a sliding window technique with a window size of 250 milliseconds and an overlap of 200 milliseconds, resulting in a new analysis window every 15 milliseconds. A set of four time domain features, including moving average value, slope sign changes, waveform length, and integral EMG, were calculated for each analysis window. The TD features were chosen because of their excellent computational cost and wide academia acceptability. The extracted features corresponding to a certain motion class are shown. The extracted SEMG features were used to train and test an SVM and an LDA classifier. The SVM classifier was utilized with an RBF kernel. The parameters cost and gamma were chosen based on exhaustive grid search and tenfold cross-validation. The entire programming was done in R language. Training and testing datasets were independently formed by randomly dividing the data of each motion class into equal training and testing data. The training and testing data of individual classes was then combined to form the training and testing data sets. The confusion matrices of the two classifiers are shown for the distant taxonomy motion classes. The SVM achieved an average classifier accuracy of 98.1%, while the LDA achieved an average classifier accuracy of 95.2%. For example, the leftmost column for the SVM results shows that 99.3% of the test samples corresponding to motion class close were correctly classified, while 0.6% were incorrectly classified as extension and 0.1% were incorrectly classified as flexion motion class. The confusion matrices for the closed taxonomy are shown. The SVM achieved an average classifier performance of 96.5%, while the LDA achieved an average classifier performance of 89.9%. When the classifiers were trained with the data of all the 16 motion classes, the confusion matrix for only the SVM is shown. The SVM achieved an accuracy of 96.5%, while the LDA achieved an accuracy of 88.5%. A performance comparison shows that the LDA showed a significant performance difference for classifying the distant taxonomy and the closed taxonomy motion classes, while the performance difference for the SVM was insignificant. A comparison of the SVM and LDA classifiers shows that the SVM performed significantly better than the LDA. The performance difference is more significant for the closed taxonomy group and also for the combined classes. A class-wise comparison of the two taxonomical groups shows a significant variation across classes. This is because some of the classes are more overlapping in feature space as compared to the others. A subject-wise comparison of the classifier's performance shows a significant variation across individual subjects. Now, this is expected since the muscular physiology is dependent upon the daily life activities, which may differ across subjects. It is interesting to observe that the performance variation is more pronounced for the closed motion classes as compared to the distant motion classes. Another important aspect was to study the variation of classifier accuracy with the varying number of SEMG channels. It is evident from the graphs that the closed taxonomy motion classes are more severely affected as compared to the distant taxonomy classes. This is an important finding since most of the commercial prosthetic systems utilize a pair of electrodes for real-time prosthesis control. Now, these are the main conclusions of this study. Classifier performance has a significant dependence on motion class taxonomy. Linear decision boundary classifiers are more significantly affected as compared to classifiers with non-linear decision boundaries. Taxonomical effects vary significantly across subjects and classes. Classifier performance dependence on SEMG channels is more significant for the closed taxonomy classes as compared to the distant taxonomy motion classes. Now in future, we are planning to study the arm position effect on taxonomical groups, and we are also interested in studying the taxonomical effects on dynamic grasping movements. Thank you very much for listening.